Hello and welcome to the course of classical motion of a single particle. So, in the last time we were discussing different aspects of classical mechanics as a dynamical theory. We also said that in classical mechanics the basic idea is to know the position and the velocity, and more broadly if you know the position and the velocity at a given instant, then using that you have a set of equations of evolutions for position and velocity. You can trace the particle and its state of motion at a posterior moment, right. So, this is the basic goal of classical mechanics. Then we said that the basic equations are given by the Newton's laws, and if you really write the Newton's laws in a smarter way, and then you can actually see that in classical mechanics you have two dynamical variables. One is the position, another is the velocity. The position, sometimes I can also write x vector as well, but I will write r for being a little bit more general, and this is the velocity vector, and in general you know that r dot is equal to v. Then this is the definition, and up to this we said this is kinematics, this is describing the motion, and then the second one is v dot, where basically your dynamics comes, where you are trying to explain the motion and where basically you are trying to relate the motion of a particle with something external, which is a force. Okay. And this is Newton's second law, this one Newton's second law, and here m is the mass of the particle and f is the force exerted, and so you can actually see. So, this is the set of equations which we have to solve. So, this is a set of coupled first order differential equations, ordinary differential equations, and because there is no partial derivative, and of course, if you can write in a more compact way, you know this is equivalently can also be written as r double dot is equal to f over m, which is another equivalent second order or ordinary differential equation. In both cases, as I mentioned last time, that we need two initial conditions, and if you know two initial conditions, okay, most preferably one for x and one for v at some t is equal to t0, then you can actually accurately predict in classical mechanics the position and the velocity of a particle, given the condition that you know the force, you can trace the particle, that means the position and the velocity at any posterior moment, or even actually any moment which is meaningful. Okay. You cannot of course try to trace the particle before t is equal to 0, that is not meaningful. So, then we started doing some simple interesting calculations for one dimensional motion, and we said for one dimensional motion Newton's law is nothing but dv dt is equal to f, and this dv dt for one dimensional motion we can write dv dx dx dt, because only one space coordinate is there, and then you can write simply this is nothing but v dv dx, because dx dt is v, is equal to f. Then I can now today I can give you an example of such condition where you know f as a function of x, for example, and I say that this is very useful, this form, when you have f as an explicit function of x or v. So, I can now take an example where your force is given by alpha root x, where alpha is a constant, let us say positive constant for instance. Okay. And then of course, you can say that for this case I have v dv dx which is equal to alpha root x. Then what you can do, you can take v dv on one side and alpha root x is nothing but x to the half dx, and then you have d of v square over 2 is equal to alpha x to the 3 by 2 by 3 by 2. Okay. So, finally, you can write d of v square by 2 is equal to, so you can actually write, I have just check where I have did the thing correctly. So, yes, I should write like this. So, since I have already done the integration, I should just get rid of this, yeah. And then you can say actually here you have an arbitrary constant of integration which should appear here. Okay. And then once this is appearing, then you can say in the second step you have v square over 2 is equal to 2 alpha over 3 x to the 3 by 2 plus some c. From that, in the next step you can do v is equal to 4 alpha over 3 x to the 3 by 2 plus 2 c whole root, and that is now your dx, now dt, dx by dt, and with this is a function of. So, 4 alpha by 3 can be another constant beta x to the 3 by 2 plus 2 c, which is a constant, and then what you have to do, you have to just smartly integrate this thing, and that I leave up to you to do, and where you can have basically x, I mean you have a function of x will be equal to t, and if the function is invertible, then finally you will have x as a function of t. Finally, so you know that, then you will do dx dt to find v. Okay. So, this is the strategy for this type of problem. Okay. Now, in this case you know that whenever you do this type of thing, there will be another constant which will appear, let us say c prime, and this c, these two constants can be eliminated just by using the appropriate initial conditions. Okay. Such type of problems you will have in your assignments. I am now going to another point. Let us say I have a case where this dv dt is a constant. Let us say the force is non-zero, but it is constant. Then what happens? Then can I say something about its trajectory or something like that? So, okay, let us start with the simplest one. If c is 0, a constant but a 0 constant, okay, then I know dv dt is equal to 0 and d2x dt2 is equal to 0, which simply say that dx dt will be constant and x will be c t plus c prime, which is nothing but a linear function of time. Okay. So, in an xt plane it will simply be represented by a straight line. Okay. Now, you can say that if at t is equal to 0 my initial displacement is 0, x is 0, then simply you can say that this c prime will be 0 and you will have simply x is equal to c t. If x is equal to c t, then still this c you have to determine. For that you have to know the second initial condition on the velocity. Okay. Now, if you say at t is equal to 0, so okay. So, now you know what will be the velocity, velocity is x dot c. Okay. Now, for this case, for this particular case, x dot is constant. So, it is uniform at every instant. Okay. So, you do not have to play with this thing. So, this is constant. So, this c will be a constant and this is a constant of motion. Okay. So, this type of thing is also a constant of motion, and we will encounter a different type of constants of motion also in today's discussion as well a little bit later. Okay. So, you see then the whole solution will simply be x is equal to c t. So, it will be a straight line passing through the origin with slope c, okay, because dx dt is c. Now, I would like to do something for the case where c is not 0. So, dx dt is equal to, so d2x dt2 is equal to c is not 0, then dx dt will be simply ct, right, and there will be some c prime as constant. I will again integrate and I will find x will be equal to c t square by 2 plus c prime t plus c double prime. So, this one I know, this is my known constant, the two arbitrary other constants would come from here. Okay. The c prime and c double prime, they will come as an arbitrary constants of integration. We have to remove them, okay, and who will help us? The initial conditions. So, once again, if you say that at t is equal to 0 my x is 0, then your c double prime will go to 0. At t is equal to 0, x is equal to 0, then c double prime is 0. Then you are left with x is equal to c t square by 2 plus c prime t. And then you say, okay, this is okay, but then what is my dx dt or velocity? Now, velocity is c t plus c prime. Then you say at t is equal to 0, velocity is also 0, then c prime is also 0. Okay. If you say if at t is equal to 0, dx dt is also 0. Then finally, your final equation will be x is equal to c t square by 2. Now, you see what will be then the trajectories of the particle in x t plane. So, in both cases they will be parabola. This is a parabola where the origin is shifted, and this is the parabola which exactly starts from the origin. Now, with all these things, the final thing which I will now try to address is the case where this force d2x dt2 or dv dt is a function of velocity. So, the force is now a explicit function of velocity. The simplest case is the force is proportional to the velocity itself. I mean, I would say the magnitude of the velocity itself. So, the speed. Okay. So, what happens? See, if my dv dt is equal to kv, then I actually know that d of, if I just do a multiplication with v, so then it will be v dv dt, and that will be kv square, and then I say this is nothing but d v square by 2 of dt, d dt of v square by 2, and that is equal to k v square. If in this point, at this point, if in this position I make my k to be less than 0, you see that such a force is actually responsible for dv square by 2 by dt to be less than 0, and that means just by and on the other hand, if you choose your k to be positive, then your situation is different, then you actually find your d dt of v square by 2 is greater than 0. So, such type of force directly gives you, directly plays a role like a energy sucker or an energy sink or an energy pump. Okay. So, this is called a sink of energy, because your system is actually losing energy. So, this not this is, but I am just saying that this type of force basically says that there is a sink of energy where your energy is getting dissipated or leaving the system. That is why your system is losing energy in time, and this is mainly saying that your system is gaining energy with time. So, there is a source of energy. Okay. So, you see most of the cases when you do several experiments, for example, one raindrop is moving through air, one ball is moving through water, like this type of thing. Most of the cases you see in general properties of matter, even in mechanics, we model the frictional force to be proportional to V, and that is the case where we actually say that we have a dissipative force. So, that is why KV type of force is a force which can guarantee dissipation. Okay. Here you see I am just talking both these cases in terms of the accelerations that I can do, because in the last lecture, as I said, I am considering only a particle with constant mass m. Okay. If the mass itself is a function of t, then this case would not be that convenient, then you have to take the whole thing. But here I can simply say that mass is a constant. So, even if I have a mass over here, I can just have to redefine the constant to be k prime, let us say. That in this motion I just said that for example, when in the motion you have a force is constant. So, that means this constant is true, this constant remains constant throughout the motion. So, this is a constant of motion. Okay. Then also when I say that okay, the force is 0, then velocity is a constant. Okay. This is a constant of motion because this is also remains constant throughout the motion. Now, in general there are some other constants of motion which are a little bit of different type. I will not exactly penetrate into that now, but somehow they will also come out. So, you see that if we have a constant of motion where you can, when you write the constant of motion. So, for example, here you can write this that this V is equal to dx dt is equal to Ct plus C prime, and C prime is equal to 0. So, you have a constant of motion of type of like this. So, this type of constant of motion, they just ordinary constants of motion. But if we have some constants of motion which are coming as a result of some integration, then we also call that as the integral of motion. Okay. And the basic difference between a constant of motion and an integral of motion is that in an integral of motion, the time does not appear explicitly. Okay. So, this is something which we will talk a little bit later. I am now somehow trying to give you another a very basic example of an integral of motion. So, let us say I just said for a one dimensional motion you have m dv dt which is equal to f. I now say what happens if f is, so this is a scalar because this is 1D, everything is scalar over here. If f is the ddx, the space derivative of another scalar function, it is not impossible. We will just ask this question, what happens if we have this? Do we have any interesting thing? So, the first thing is that what you can say that yes, you have to just look this thing a little bit more carefully. So, m, if I say that this is v dv dx, that I just said some while ago, that dv dt is nothing but dv dx dt. So, this is v dv dx, and I simply now said okay, let us do something a little bit more attractive so that people can relate. I would say f is not dv dx, but it is minus dv dx actually. Okay, no problem. This all depends on how you define v. Okay. So, I can write that. So, this is m small v d small v dx is equal to minus d capital V dx. What happens? I would say this is nothing but d dx of half mv square, and this one is minus v. So, it will also come to this side, that will be v and that will be 0. Okay. So, you see that this d dx of this thing is 0. Now, if I simply say d dt of half m v square plus v, then that will be actually, so I will have some dt dx is equal to 0. And what is dt dx? This is 1 by v. Now, if I consider a motion, which is where, I mean, it is most reasonable to consider the v not to be equal to 0. Otherwise, there is no, I mean, no meaning of studying the motion. Okay. So, 1 by v is not equal to 0, and that is why this should be 0. If that has to be 0, the whole thing, the product, say, then this should be 0, and that means this half mv square plus v is constant in time and also in space, as you have seen over here. Okay. In 1D both are same, no problem in there. Okay. And what is this? This is, we know, the kinetic energy of a particle, although we have not defined in this class till now, but this is a part which is kinetic energy, and this is a part which we call potential energy. Okay. And this scalar function whose space derivative with a minus sign is the force, we call that as a potential function. Okay. So, you see, if this is the, if f is equal to minus, and the sum of these two, sorry, that is what I was trying to say, the sum of the two, they are always keeping constant, although individually they are not constant in time or in space. Okay. That is a very good information. Now, what exactly is this and what exactly this is? So, what I just said, that I have a mathematical conclusion. So, that I will discuss later. So, the first thing is that you know that the sum of two things, they are constant, and you will also see this constant does not contain time, the time explicitly. Of course, time is there through velocity, through v, through v is a function of x and x is a function of t. So, always all of them are intrinsically or implicitly depending on t, but t is not explicitly appearing, and that is why this is known as an integral of motion. Since I have this relation, I can actually back calculate to find v. So, if I say what is v, v is nothing but minus integration f dx. Okay. You will always see there will be a play of an arbitrary constant like an initial potential or a boundary potential that you can choose at your convenience, and it is the difference between this I mean difference of this v values between 2 points which are actually of importance in physics, because if you understand that finally the dv dx, which I mean associates dv, is actually something which is giving us the dynamics. Okay. So, you see that we have two things till now, we have two conservation. One is when the force is dv, I mean force is equal to m dv dt is 0, then mv is constant. That is very evident to see, and another constant is, now if we have the force has this type of nature, then I have another constant. This is very general, this is not general, for that you have to have a force to be of this nature. Okay. Finally, a smaller one, another conserved quantity or another constant of motion we have to search for, and before doing that, maybe it is good to just tell you. So, what is this? This is called the linear momentum conservation. Linear momentum conservation, and this is the conservation of energy. Actually, it is called mechanical energy. Okay. Now, at this point I will just try to say one thing, that if you now increase your dimension of motion, the dimension of the whole thing to be more than 1, then of course you do not have this dv dx, then you have to have something, a more general expression for that, and for that what I was trying to say, that I have to need m dv dt, which is equal to then f, which can be coming from all the spatial differentiations, or all the space due to the space variation of all the spatial coordinates. Okay. And so, for that I have to somehow generalize this expression. So, one can easily show that what is this, then you have to, so in 1D, if this is minus dv dx, this is a capital V, dv dx, then x cap. Okay. In more than 1D, let us say in 3D, where you have 3D Cartesian system, then you simply have minus del v del x, x cap, minus del v y, y cap, minus del v z, z cap. Okay. If you have this, then actually you can say, okay, this is nothing but minus, I have this del x, x cap, plus del y, y cap, plus del z, z cap, which is acting on V. Now, what is this? So, what is this first of all? This is the change in V, change in the scalar potential function when you are changing infinitesimally your x coordinate. This thing is the combination in more than 1D, let us say in 3D, this is the combination of 3 terms. This one just saying that you are only changing infinitesimally x coordinate, and you are keeping y and z coordinates to be constant, and you check how V is changing only with x. This is the same for y, this is the same for z. If you combine all the effects, then finally you will have this. In general, we denote this thing by a nabla sign. So, it is a minus nabla, which is itself a vector operator, vector differential operator working on V. Okay. Now, if you see, if I just take this thing dotted with this thing dotted with dr vector, where r is nothing but the position vector, then I have a very interesting result. Then you have del v del x, x cap, plus del v del y, y cap, plus del v del z, z cap, dot dx x cap plus dy y cap plus dz z cap. If you do the calculation, what it gives, since this is a scalar product between two vectors, what do they give? They give simply del v del x dx plus del v del y dy plus del v del z dz. And if you know the rule of chain rule of partial differentiation, this is nothing but the definition of a total differentiation d of v. Okay, d of v. That is exactly what we will use for what we will use for defining the something like another conservation of something like a conservation of this type, conservation of mechanical energy in more than one dimension. Okay. How to do that? How to do that? So, we will start by saying that okay, I have m dv dt, and that is equal to, now what I was just saying is that minus gradient of v. That is my assumption. My force is in this form. Okay. I will write both sides v dot. So, I can say like this, no problem, and this one I would write this dot dr dt, because v and dr dt they are the same thing vectorially, right. This is m a ddt of, I would say this is ddt of m v square by 2, and this is, you just have seen this part is nothing but dv dt. So, you have ddt of m v square by 2 plus v is equal to 0, and you have m v square by 2 plus v to be constant even in more than one dimension. Okay. This is known as once again kinetic energy, this is known as potential energy. Okay. Here our assumption is v is a function of the space coordinates only. Okay. With this I just wrap up this lecture. So, in the next one we will discuss some more properties and some more conservation principles, okay, regarding this type of motion. Thank you.